So, hi everyone. I'm Davide. I'm a PhD student from Politecnico di Milano. I'm part of the Deep Space Astrodynamics and Research Technology group there. And today I'm going to present you something I've been working on during my PhD. A bit of a context about that. So there was very nice talks these days about autonomy, why we need that, what's going on for the future, and etc. So I don't want to stop on that. I'll just say that when you want to implement autonomy, there's something that you have to reason about. That is not only to implement methodologies regarding guidance, navigation, and control, but you want to go further in that, and you want to develop a software that leverage that autonomy. And you want to bring decision-making on board. And when you do that, then it becomes very complex to perform validation and verification activities on that. And so why can't we have a software architecture that may help also in this? So I'm part of the Extrema project, which is a European Research Council funded project, 5 years. It's coming to the end this year, actually. And the project wanted to develop technology, GNC technology, to make spacecraft able to independently fly in interplanetary space. Some of the concepts developed in Extrema are autonomous navigation based on optical triangulation of planets, autonomous guidance. We have different techniques there. They're all based on low trust guidance. And then autonomous ballistic capture is, for instance, about orbiting Mars. The idea is that once we develop the algorithms, that we're also able to validate them. And how do we do that? Through hardware-in-the-loop experiments. And so we have an experiment for each pillar. The idea is to make these experiments together in a hardware-in-the-loop facility that is the Extrema Simulation Hub. And there's a nice schematic. It's real. I'll show you pictures of that, but this is more informative. And we have different components of the facility, and you can imagine of the facility as a spacecraft whose subsystems involved in GNC are represented as test beds. So we have thruster test beds, optical test bed, attitude test bed, etc. And then we have some simulator for the environment, and we have also a processing system that is organized as a flat set architecture. And on this system, we're actually running the software I'm talking about. So I said that we would like to have a software that help us to implement autonomy. And I'm talking about deliberate autonomy, and at the system level, not only at a functional level. In addition to that, we would like also to reduce that lead time that takes an algorithm from the actual mathematical development to space. And in order to do that, we want to have a highly modular software and an agile integration of the algorithms. At the same time, we want to have that also in a hardware context. And plus, we would like to have our software also be able to help in performing V&V activities. So supporting testing in a facility and different testing frameworks, such as software-in-the-loop, processor-in-the-loop, hardware-in-the-loop. So to a certain extent, we don't want also only to have GNC flight software, but we want also that flight software is a flat set software. The architecture is very classic. It's a 3 layers architecture. We have a middleware, an application, and a hardware layer architecture. But what are the principles behind? So we wanted to explore some of the modern principles in programming. And this, unfortunately, requires a bit of heap memory allocation. But this is fine because it is research on some extent. So we rely a lot on high-level abstractions, but at the same time, we want to have some low-level control. And modern programming techniques brings you also that. We exploit a lot of software patterns because we believe that they improve a lot code explainability And this helps you in understanding the code. So some of the pillars that characterizes this software are modularity, configurability, and concurrency. And some of the paradigms used are object orientation, event-driven execution, and also real-time. Okay. So as a language, we use C++, 20 standard, because it allows you to have some core new functionalities to explore. And actually, we use, for the math in it, we use a mathematical library that was developed within ECSS related project at ESA, which is libmcs, which is pre-qualified, which is a good thing. Some of the parts of the software I'm going to show you are migrating to Rust. And migration means not that we copy paste code and translate it into Rust, but Rust requires actual refactoring of how about the philosophy behind the modules itself. So some of the features that are nice about meta-programming instead are compile time evaluation of expressions. We use a lot of templated classes, which allows you to have code that you can reuse a lot, and also a lot modular. And we use constraints and concepts. This allows us to outsource some part of the code to people that are not really a lot of expert in C++ programming, but they may have some small modules developed to the level. And it's a way to constrain them in design the modules in some way. As I said, large exploitation of software patterns. Here there's a list, but I'll be more clear in the next slides. So I said we exploit concurrency. How do we do that? Well, again, some heap memory allocation again. Why is that? Because at some point we thought that as a research project, it would be nice to explore new functionalities and give up a bit of real-time safety in the software. And this is the reason why, for instance, we have some tasks that are implemented through coroutines, which are nice because they are nice because they provide you an easy way to control the granularity of the execution of a function so that you can return to the caller at any point. But at the same time, they lack of real-time safety, and because they use heap allocation. And so we also compare them to the use of more traditional thread-based execution of tasks. There's a use of smart pointers, of course, but not as just throw everything as a smart pointer, but with a philosophy that with the smart pointers, we want to really control the ownership of the objects that we associate with that. Okay. This makes VNV activities, of course, more complex, but again, it's a trade-off, and it's a good opportunity also to understand, okay, how then can we deal with multi-threading in VNV activity? Okay, so now getting a bit more into detail of the architecture. So the driver of the architecture was how we can conceive an autonomous system. And one of the ideas is to conceive that as composed by a reasoning core and a reasoning context, where the reasoning core is actually hosting the elements that perform decision-making, while the reasoning context provides you the data and the sensing, if you want, and also the actuation of the decision that you make. We want to have autonomy configurable in terms of guidance and navigation. And we achieve that by different management policies of guidance and navigation functionalities. Currently, we have tested timed policy, which is very classic, not really autonomous, reactive policy, and we're working on deliberation as well. you may recognize some elements of other frameworks. We have tons of frameworks, which I think is very nice because they come from different backgrounds. And so you'll see some of them. The most used one is Fresco framework from JPL. And yeah, so we have some, so talking about the reasoning context, it is composed by mainly two layers in the software. That is the application layer and the hardware driver layer. So in the application layer, you find all the algorithms that some GNC expert developed. And the hardware driver layer provides just the software to interface with hardware, which can be of many types, as I'll show you in a while. And then we have the middleware layer that instead is providing you it's a bit different rather than from the classic concept of middleware layer, and is actually providing you not only the link to the operative system behind the software, but also but it hosts the core components of the decision making on board. What are those components? GNC planner, a task executor, a event handler, and a time orchestrator. The GNC planner is basically relying on a state variable estimate database, which is a concept from the Fresco framework, which provides the data on which you can take a decision. We have a task executor because once we know what we want to do on board, then we want to schedule it and execute it. And this is the purpose of this second element. And then we want it to be event-based. And we have an event handler loop that takes care of catching up the events generated by the functionalities, the tasks on the software, and react on them. And it is as modular as possible so that we can plug new events easily and handle them. Finally, we have a time orchestrator. You may say it's not really interesting at having a time orchestrator because time is very important. The software is something that is, I mean, it's always there. The reason why we have a dedicated time orchestrator is that we don't have always the same source of the clock, which is not always the clock on the board on which we're running the software. This concept comes a bit from ROS too. I'd say, in which you have a node that provides you clocking. In this case, well, not clocking, but timing. In this case, we can interface to a hardware clock, a virtually accelerated hardware clock, a system clock of any type, but we rely always on the same calls inside the software. And this is very important because when you develop the software in the Extema Simulation Hub, for instance, and you rely on an accelerated virtual clock, and then you go on board, you don't want to change the functions that call the clock. So this interface provides you this capability. Okay, so just a small focus on the planner, GNC planner, how it works. This is really conceptual. It's not really actually working like this. It's more complex. But imagine we are navigating in deep space and we want to look at different planets in time. So there's an expert that is the navigation expert that provides you planets to look at as a schedule, as a priority queue, let's say. And from that, you derive the tasks that has to be executed. And the call to the GNC planner, which means how many times I have to reason on which planet to look at, can be periodic or event-based. Okay, so I talk about GNC algorithms. Putting them together is really complex. We discussed about that with some people yesterday and previous days. So how to make this easier? We abstract the modules doing that. For instance, we rely more on the functionalities, and we ask ourselves, okay, the functionality that we want to tackle is what trajectory am I flying? And this is a functionality that is achieved by the estimation algorithm boards on navigation board, right? So we have a module for that. And the module can have different strategies because we can have different algorithms that can perform this estimation. And the same applies for the guidance. And in order to do that, we exploit a strategy pattern. We provide the capability to interface algorithms that are written in C++ code and C code, but also that are auto-coded from MATLAB. And in order to do that, in addition to a unified interface that provides this capability of the strategy pattern, we have also adapters. And the reason is that you don't have a one-to-one conversion from all MATLAB generated structures with the structures that you have on board. So class adapters help a lot in this. Okay, so last layer, the hardware one. We have interfaces that look like the one that I just presented because they use the same pattern, which is the strategy one. And here we add also state machine because the hardware module we connect to can be represented as a state. It is in it. And we can have, for instance, the thruster module, the camera module, and we can have, instead of like strategy of trusting or taking pictures, we can have different models of these elements. For instance, mathematical model, test bed, or a real camera. The communications protocols that we use so far are the interprocessing communication with tunnels, with other processes. We use wired and wireless sockets, and they rely a lot on protobufs because they're very nice because they provide you a common knowledge of the structure you want to describe, and you can translate that into different languages. So from the same protobuf description, you can generate a C++ structure, a C structure, Rust structure, etc. And an SPI, of course. Okay. So configuration and reconfiguration is a really hot topic, I'd say, because you want to have a software that can adapt, and this part of also of some autonomy, can adapt at runtime to different conditions, or if you want to change something into the software at runtime and at boot time. In order to do that, we exploit schemas, which provide you a standardized way to describe the input files that you can provide to the software, in this case, JSON files. And we also experimenting some adaptability in the kind of, like adaptability in the sense that we infer, for instance, the autonomy level that we want to achieve. So for instance, the GNC planner can reason more or less depending on the definition of the duty cycle for the guidance and navigation that we provide. And we can also bypass some functions on board depending on the runtime executions. And this is thanks to the patterns that I presented before. Okay, this is a typo because I forgot to remove that, but okay. So the software was deployed on, we are running it actually on an UltraScale Plus. The very first board was a Raspberry Pi, then we moved to this. And it is supported by a Linux. So the background OS is a Linux with a preempt RT patch. The good thing that we have implemented to accelerate the deployment on the boards is a CI/CD pipeline that takes care also of cross-compilation of the software, which is always complex and takes a lot of time. And this accelerated that a lot. We're calculating it at different frequencies. The UltraScale Plus allows you to do that so that we can test it. For instance, we can have more reasoning about the execution time of some functions, of some GNC functions, or we cannot care about them at all. Okay. So a second deployment was actually inside the External Simulation Hub. This is a picture of it, the glass cube, in which you see the different test beds that we have. And this is a kind of simulations that we run in it. This is what's happening in a schematic way inside the simulation, where the planner, in this case, is a reactive one. So we interface with the different facilities, asking for pictures or commanding trust arcs. And the software helped a lot in accelerating not only how fast we can integrate the GNC algorithms and different GNC algorithms into the framework, but also how fast we can integrate different facilities and hardware. And finally, presented a poster about that yesterday. Elapse software was the software supporting an experiment that we ran on OPSAT last year, which was about taking the algorithm of developed in Extrema and try to run them on board, acquiring real images and perform evaluations so evaluate their performances on board of a real spacecraft. Nice thing was that thanks to the modularity of the software, we were able to downscale it in a very fast way and make it very light to be deployed on OPSAT. Okay. So coming to the conclusions, so Elapse was conceived as a software providing capability for both as a flight software prototype, because you may say this thing is not ready to go on a spacecraft, and I totally agree with you, but it's a nice way, it's like a gym to provide, to test new functionalities and also to test new testing methodologies to test those functionalities. At the same time, we have a software that is dedicated to GNC and can be deployed potentially on board for autonomous operations. Border programming techniques help a lot in improving your code explainability, flexibility, and agile interactions of the algorithms and of the hardware. And I demonstrated you different deployments that we achieved thanks to that. Future work, this is very limited, a very limited list. I have, I think, a book of things to implement in the future. But I think some of the most relevant ones are automation of the GNC algorithms integration into the software. This is not automatic at the moment. And introduce that into DevOps environment. Deliberation in the GNC planner is an open point. I'm working on it in my actual research. And then we would like to push more on Rust integration of the whole middleware layer, and also run that not only on Linux, but also other real-time operating systems such as R10s. So thank you for your attention. And if you have any questions, I'm here. And I invite you to visit also our website and get more insights about Extrema project.
Thanks. Let's give a hand to Davide. Question time.
Behind you.
So basically, if I were to summarize, could you go back to your architectural slide where you had a core and content block diagrams? Right. So I think you're trying to, I think we used to call it kind of separation of concerns. You're trying to separate all the GNC algorithms in the kind of the middle layer, but the core is the one is really executing and planning using the multi-thread techniques. Is that what you're trying to accomplish?
Yes.
Did I say that right?
Yeah. So the reason behind that was we had the algorithms, we developed guidance algorithm, we developed navigation algorithm, but then how do we coordinate them? And the coordination of them, both at the execution level and both of that, came to the
Core.
To the core. Yeah.
Yes. All right. Thank you.
Thank you very much.
Any other questions? All right. Well, let's once again thank Davide.
It's